or z. So the only possibility is epsilon x z y dx wedge dz wedge dx dy, right? I'm already done with two terms because each of those like expand into 3, but 2 of those are 0. So I need not to worry about that. So, okay, what is the value of mu over there? What is the possible non-zero value of mu over there? Like,
it's Z again.
Z again. Okay, so here
X.
here
Y.
it's y, because z and x are already taken, right? What about this one?
X.
Epsilon z y x dz wedge dy wedge dx, right?
Yeah.
Now it will be helpful for the later cases. That's why I'm showing this trick at this stage. See one thing. So you have the sequence here like x, y, z. Here epsilon x, y, z is +1, right?
Yeah.
And then you have like dx wedge dy wedge dz. I think I made a mistake over there. I should write like dz over there. Okay. Okay, now if you write that term, that gives you like 1/6, that's fine. Then epsilon xyz is +1, and you're left with like dx wedge dy wedge dz. That's fine for the first term.
Yeah.
Now for the second term, instead of like substituting epsilon explicitly, do this thing. If you switch these two wedge products, like if you make it like dx wedge dy wedge dz, you get a minus sign, right?
Yeah.
And also if you switch these two things, that will give you a minus sign as well. So overall becomes plus, and overall this term and that term are the same term, just repeated twice, written in two different ways.
Yeah.
What about this thing? Can you do the same trick with the third term as well?
Yeah, we can.
Switch such a way that it matches with the upper like these wedge products. So to do that, you switch these indices first, like dx and dy first. That gives you a minus sign, and that minus sign is absorbed by switching like xy yx over there, and you get the upper one, right?
We get the sixth term, same term.
Sorry, we get
Sixth same term, like
we get
dx
same
with
terms. Yes, exactly. So this is just dx wedge dy wedge dz. Okay, so just final one thing. This kind of algebra is it becomes really easy when you consider this symmetry inside of it. So whenever you have like epsilon, let's say kappa lambda mu, and like dx kappa wedge dx lambda wedge dx mu, remember if you switch any of those two indices over epsilon, it gives you minus sign, and same thing is true for over there as well. So basically, this thing is nothing but same term, like how many indices are there, that much factorial, that is 3 factorial times just written in sequence, like epsilon xyz dx wedge dy wedge dz, like that. And this applies for every antisymmetric summations. So remember this thing, this result, like epsilon kappa lambda mu summed over dx kappa wedge dx lambda wedge dx mu is basically 3 factorial epsilon xyz dx wedge dy wedge dz, which is 3 factorial dx wedge dy wedge dz in Cartesian coordinate, because like, yeah, your epsilon xyz could have like metric tensor part inside of it, so yeah, it could be something else as well. So in Cartesian coordinate, that's true. Well, like this result is true in Cartesian coordinate, but generally this is true already. So just remember. So whatever what did you get from this this thing, like the result? Hodge dual of what we have been seeking for, like what is the question that
One.
is the result? So
Hodge dual of
star of 1 is what that we have been seeking, and we got dx wedge dy wedge dz.
Yeah.
Okay, so question is, what should you get when you do this thing?
One. It should be proportional to that.
It should be proportional to 1. Yes. Actually, for 3 dimension in Cartesian coordinate, you'll get 1. That's true. But we'll have a relation like double star. What happens if we do this on anything? Is it generally 1? Answer is no. It depends. It depends on the metric tensor itself. So we'll see. We'll derive this result as well. Like not just this result. Like there should be some factor, plus or minus factor. So okay, I think I should take a break a little bit. Then I'll just do this last thing. Sorry.
What did you say this last time? I skipped.
Oh, I said that our, like we can see it from there, like star 1 is basically dx wedge dy wedge dz, and our guess is if we take Hodge dual on dx wedge dy wedge dz, we'll get 1. And this is true actually. You can do the algebra and you'll find this. We'll see that in a moment after the break. So question is, basically that's doing star twice on the same thing, right? Like substitute this thing over there, like that's basically doing Hodge dual twice on 1 and getting 1, right? So probably you could incline to say probably this is a general result, like if you apply Hodge dual twice, you just get 1, which is not true. Basically you'll have some factor over there, because in 3-dimension Cartesian coordinate, that's true. This thing is true in 3-dimensional Cartesian coordinate. This is true, but generally it's not. In general, you'll have some factor over there. That's what I'm saying. We'll prove this result in with absolute generality. So let's take a break. I'll come back in 15 minutes. Hello.
Okay.
Thank you.
We are almost done with this Hodge dual part. We can actually start integration like within, like 2 things we need to see actually. After that we can start. Okay.